Hello everyone, welcome back to the Computer Networks lecture. In this video, we'll try to explain the link state routing algorithm. Okay, so first we'll try to explain the principle behind the algorithm, and then we'll go with the example. Okay, so first, as we have said before in the previous video, it lies under the centralized routing mechanism. It doesn't mean that there is a central entity that compute all the least cost paths and then distribute the computation results to all the nodes, but it means that all the nodes in the network has the global view of the network topology, and all the nodes have the same information about the path, okay, the cost path between nodes, and this is all accomplished via link state broadcast. And also this is, I mean, all this information has been obtained by each node before the Dijkstra algorithm is run. Okay, so Dijkstra algorithm is run to compute the least cost path. Okay, so basically if you already pass the SDA, the data structure and algorithm, then you have already familiar with the Dijkstra algorithm. All right, and in this algorithm, the task is that every node computes the least cost path to all the other nodes in the network. So, for example, like if we have 5 nodes in the network, A, B, C, D, E, node A has to compute the least cost path from A to B, A to C, A to D, A to E, and also for B, C, D, and E. Okay, so B from B to E, B to A, B to C, B to D, B to E, and so on and so forth. Okay, and then the result of this is that every nodes will have the forwarding table. Okay, so for example, like the purpose of this forwarding table is for forwarding in every node. So for example, like if A receives the packet, and the packet is the destination of this packet is to node C. Okay, so it knows where to forward this packet to. Okay, all right, and then this is going through iterative process, and each iteration will find we will get least cost path to one node. Okay, so let's say we try to find let's say we take this example, the previous example, we have A, B, C, D, E. So we'll try to find the least cost path from node A. Okay, so basically we will have 4 iterations. Okay, because we'll find least cost path from A to B, C, D, and E. Okay, so basically the total of iteration will be 4, and in each iteration, we'll find the least cost path of one destination from A to any one of the destination. Okay, so basically after k iterations, we'll find a least cost path to k destination. All right, so this is the notation of the Dijkstra or link state algorithm. So we have Cx comma y, this is comma y. This is the direct link cost from node x to y. As we have said before, if there is no direct link, then the cost will be infinite. Okay, and this is the dv. dv is the current estimate of cost of this cost path from source to destination v. This is dynamic. I mean, it's changing over the iteration. If we find the last number of dv, then we'll update this dv. Okay, and then there is pv. pv is predecessor node along path from source to v. So for example, like we find from x to phi. Okay, so from source to phi, let's say the source is x, and phi is the destination. So what is the predecessor node of phi if we go from the source? Okay, so for example, like to reach phi from the source, we'll have to go through x, for example. So x will be the predecessor node of this phi from source to phi. We'll see later with the example. Okay, and then there is a set of nodes whose least cost path definitely known. So I mean, all the nodes that we already find the least cost path, we will put it in this set n prime. All right, so let's go with the pseudocode. Yeah. Okay, so before we start with the initialization, So for example, we want to find the least cost path from node u to all the other nodes. Okay. So first we add this u in the set of least cost paths. Okay, so n prime. Okay, and then we'll check all the nodes v. V is all the other nodes in the network except node u. If v adjacent to u, so basically we try to assign the temporary least cost path from u to v. If v is adjacent to u, or it's direct neighbor, or it has direct link, then we can directly assign dv with the cuv. So v is any node that is adjacent to u. Okay, but it may not be minimum cost, so we'll evaluate in every iteration. But if there is no direct link to u, then we assign dv with infinite. Okay, so we'll go with the iteration. Find w not in n prime. Okay, so if the node is already added in the n prime, we'll exclude that node in the loop. Okay, we compute the dw. So basically we'll try to compute from the least cost path from u to w. W can be any nodes which is not in the list of n prime. Okay, so if we find that dw is minimum, then we add w to n prime. So we add, for example, like u and then w. Okay, and then we update dv for all v adjacent to w and not in n prime. So basically because before we only know the direct path. So for example, like we start from the initial node u. Okay, then we only know let's say, for example, the direct path, and then we find another node, we find another path going to from u to v through w, for example. So for example, like this is u and then v. Okay, so it has direct path, and then there is w here. So in the first iteration, we find that the cost path. So for example, the cost path from here u to v is 5, and from u to w is 1. Okay, and the cost path from w to v is 2, right? So then we try to move one step to w and compute what is the cost from w to v. Okay, so for example, in this example, it is 2. So now we take the minimum, okay, between the direct path, so or something that we already know before, dv was 5, and then we just know that the cost path of dw is 1, and then the cost path from w to v is 2. So we know that this is the minimum cost. So now to go to v, then we can go from u to w and then go to v, and then this process is done iteratively until we find all the nodes in the, until we cover all the nodes in the network. Okay, now let's go with the example. So we have 1 2 3 4 5 6 nodes, and we try to find the cost path from node u. So for example, this is the original node, and then we have to find the cost path, the least cost path from node u to v, w, x, y, and z, right? So first, the initialization step, because node u has direct neighbor with v, x, and w, then we can assign already the cost path, the temporary least cost path from u to v, w, and x. Okay, because they have direct link cost. Okay, but for y and z, because we don't have any direct link from u to y and z, then this is infinite. Okay, now so in the first iteration, we try to find what is the minimum least cost path, okay, from u to any other destination, v, w, and x, and we find that x has the least cost path from u. So now we take this node x and add it to the n prime. Okay, And then in the next iteration, we'll exclude x from the iteration, okay? And now we can go one step to x. So basically now we already have from u to x, we know there is the least cost path from u to x, okay? And then from x we can go to the other nodes, okay, that is adjacent to x. Now we find one more path, okay? So y is the neighbor with x, and we can evaluate another route from x to the other v and w, okay? Now all right, so in the second iteration, from u to v, we can have two options, whether we are going directly from u to v with the cost 2. And if we go from u to v via x, then we have the total cost of 3. So the initial number is, the initial pass is still the least, it has the least cost pass, okay? 2 with 2 from u to v directly. So oh yeah, and I forgot to mention one thing. PV is the predecessor node. So in the initial step 0, all the path has the predecessor node of u, because it is going directly from u, okay? But now in the second step, or in the second iteration, for example, from x to w, okay? So if we are taking the direct path, the cost is 5. But then if we take the path from u to w via x, okay, we get the total cost of 4, which is less than 5. So now we update the least cost path to w with 4, and the predecessor node from w is x, okay? So it's not u anymore, but it's x now. Okay, now we also find one more path, new path to y with the predecessor node of x, and the total cost from u to y via x is 2, okay? 1 plus 1 equals 2. Okay, now we have tie conditions here. So basically, in the second iteration, we find that v and y, they have the same least cost score, or least cost okay, least cost path score, or least cost path number. So in this case, we can take any of those v or y, and it's okay. But in this example, we take y first, okay? So we'll see this kind of path, okay? Why we take the y first? Because then we'll find another one new path, okay, to z, okay, from y to z. But if we just take v, we don't get any new path, okay, to a new node. All right, so we take y in this case, and then we exclude y in the next step. All right, again we compute the least cost path from u to v, and still this is the least cost path, so we keep it as it is. And now we find a new path to w, okay? So from w, if we go through x directly, then previously it was 4. 1 plus 3 equals 4. But if we go to w via y, the cost from u to y is 2, and the cost from y to w is 1, so the total cost equals 3. So we find a new least cost path for the path from u to w. All right, and then we also find another new node, in the path from u to z, okay, through y, okay. Right, and then in this iteration, the v is has the least cost path from u, so we take this one, okay. We take v to the n prime list. All right, now we have this finished with the x, y, and v. Okay, now we are left with W and Z, and it seems that there is no other changes. Okay, it's still the same because it is, yeah, this is the only, optimum cost from U to W. If we go from U to W via V, then the total cost will be 5. Okay, so we keep it as it is, and we add Y now to the n prime list, and then now we are left with only Z. Okay, and there is no change with the Z, so this is the last node to be added in the n prime list. All right, so this is the process of computing the least cost path by using Dijkstra algorithm, and at the end of the day we'll get this this kind of path, okay, from U to all the other nodes in the network. So first we go to V, either we go through V or we go through X, okay, and then from X go to the other nodes in the network. And if we have to create a local forwarding table, then the forwarding table will be from U to all the other destination V, X, Y, W, and sorry, it should be Z. It's typo here. Okay, so from U to V, it will be forwarded directly to V, and then from U to X, it's directly to X, and then to to Y, W, and Z, all the traffic, all the packet will be forwarded through X. So yeah, the forwarding table, there's only two options: either go to V or go to X, and eventually that all the other nodes will be forwarded through X. Okay, so we take another examples. Now we want to still the same topology, not the same topology, but same set of nodes U, V, W, X, Y, and Z. Okay, but different topology and different link costs. So first, from U we have direct path from U to W to X and to V. Okay, okay, so from U to X, the cost path is 5, U to W 3, and U to V is 7. So we take W, okay, as the least cost path in the first iteration, and then we take W to the n prime. All right, so now we have one step to W, and then we get a new path through Y, which is unreachable before. Okay, now we can compute a new cost path from U to V. If we take direct path from U to V, it costs 7. But if we take the path through W, then the cost path will be 6, which is cheaper. Okay, and then if we go to X directly, the cost is 5, and if we go to X through W, the cost is 7. So we keep the same path as before. And then we find another new node in our steps, which is Y. So the cost from Y to U is 3 plus 8, which is 11. Okay, 11 through W. Now we find that X has the least cost path, which is 5 in this iteration. So we take we take X to the n prime, and we exclude X in the next iteration. Okay, so we find X, and then we find new path to Z. Okay, and if we recompute, I think we don't have any updates. Still we have 6 cost to V through W, and then the least cost path to Y is still 11, because if we take the path from to Y through X, the cost path will be 12. Okay, so we still keep this one 11, and then there is a new path to Z when the cost is 5 plus 9, which is 14, and we get that the cost path to V has the least cost path in this iteration. So we take v to the n prime list. All right, now again we compute the remaining least cost path. Okay, y and z. So initially we find that the cost path from y to u from u to x to y through w is 11. But then if we take this path through v, then the cost path will be 6 plus 4, which is 10. Then we update this list cost path calculation to y, and we find that in this iteration this is the list cost path. So we add y to the n prime list, and then we are left with z. And then we get that if we are going to z from u through y, we get a cheaper even cheaper cost than the previous in the previous step. It was 14, now we have 12. 10 plus 2 equals 12. So we update this list cost path to z. Now it becomes 12, and this is the remaining step, and then we add this to the n prime list. Okay, so now some notes. If ties can exist, they can be broken arbitrarily. So this is what we have done before. Construct list cost path tree by tracing predecessor nodes. So basically, at the end of the day, as we have seen also in the previous example, we'll trace the list cost path from the source u to the other destination nodes. Okay, so I think we'll stop at this point, and then we'll continue some more discussion about the Dijkstra algorithm or link state algorithm in the next video. So see you then in the next video.